So, in general, our approach would be, if we have a fraction inside an integral, that we would look at the expression and see if the degree on the top is greater than the degree on the bottom. If it is, we would do long division to change what the integral looks like. And if the degree on the top is less than the degree on the bottom, then we would see if the bottom could factor and would be able to proceed accordingly. So let me do another example here. Now, when I look at this, again, first thing I check, degree on the top is less than degree on the bottom, so I can't do long division. But I look at the bottom and I see that the bottom can in fact be factored. That would be x minus 2 and x minus 1. Which again, as soon as we see that, we say this came from two separate fractions being added together, and those separate fractions were some number over x minus 2 plus some number over x minus 1. And of course, this plus, we put plus, but b could be negative, a could be negative, so it may be that it's actually minus. But for our purposes, that'll be taken care of in the constant itself. So again, we do exactly the same thing as before. I'm going to multiply this side by x minus 1 over x minus 1. I'm going to multiply this one by x minus 2 over x minus 2. And when I do that, my left-hand side, of course, remains what it was. My right-hand side, I have a times x minus 1 over these two things, plus b times x minus 2 over these two things. And of course, as before, if the denominators are the same, we will be able to add them together. That means this side equals that side, same denominators. We can ignore the denominators and say I have 5x minus 7 equals ax minus a plus bx minus 2b. And once again, it turns into a matter of systems of equations. Whatever the x terms are, and for x, I have 5 on the left-hand side and a plus b on the right-hand side. And whatever the constant terms are, and I have minus 7 on the left-hand side, I have minus a minus 2b on the right-hand side. And now I look at these and I say I have a system of two equations, two unknowns. In this case, a and the minus a, if I add these two together, they will just go away. And I'll get minus 2 equals minus b, telling me b is 2. And if b is 2, I look at the first equation there and it's quite obvious that a is 3. And so 5x minus 7 over x minus 2 times x minus 1 came from 3 over x minus 2 plus 2 over x minus 1. Then I come back to, okay, if this had started out as an integral, I've drawn that conclusion as far as how this could be rewritten. That's a big part of doing this problem, because if this came to me as the integral, I would say I don't know how to integrate that. I could look at this and say maybe I could try some completing of squares type thing in the bottom, but I really don't want to do that. And this is a different approach, and I say, okay, now that means I can break that into two separate integrals, one of which is 3 over x minus 2 dx, the other of which is 2 over x minus 1 dx. And for each of those, again, this is going to turn into natural logs. For the first one, I say I'll let u equal x minus 2. du dx is 1, which means du is equal to dx. So that becomes 3 times the integral of du over u, which is going to become 3 natural log of x minus 2. And the second one, use a different variable, I'll use v equals x minus 1. dv dx is then just 1, so that means dv is going to be equal to dx. And so that integral becomes 2 times dv over v, which integrates to just 2 natural log of v, but v was x minus 1. So the integrations themselves, once you're able to do this partial fraction decomposition, the integrations tend to be very simple. They aren't always going to be logs. If your first power under here, it's going to be a log, but you could see something that showed up with an x squared there, in which case it may go to an inverse sine or inverse trig or inverse hyperbolic trig situation. But frequently they're going to be natural logs there. I'll go through other examples where it show up with different things.